So once again, we have two great talks today. So at 2 o'clock, we have the Algebra, Geometry, Combinatorics seminar. As always, I very much encourage you to come. And then at 3, we have Amanda's thesis defense, and I really encourage you to come to that too. I'm sorry about the board looking like this. Can you read it? Let me start writing, and if you can't read, let me know. Is it okay? Can you read this? I guess you can tell. So today I want to talk about affine semigroups and cones. Okay. So maybe the first thing is to define a polyhedral cone for you. Did I do this already? I did, but let's do it again. Okay, so polyhedral cone is so you can define it in 2 ways. You can define it as, I don't know, the set of x's like this, satisfying a bunch of linear inequalities.
Here?
Okay. So that's one definition of a cone. It's an intersection of half spaces, right? So each one of these things defines a hyperplane. The hyperplane goes to the origin, and you're telling me, okay, you should be on that side of the that side hyperplane, on that side of this hyperplane, etc. Okay. I mean, maybe I should just tell you before we write any symbol. So what's a cone? It's like a polytope. It's like a polyhedron, but it should have the shape of a cone like this. So this should have oh no! Now I remember that I did kind of make this gesture a couple of weeks ago. It doesn't look like an ice cream cone necessarily. Somehow what you want is that if you have a point in your cone, then all its multiples, all the ray goes through. It's inside the cone. And you can see that in 2 ways. So first, it's something like this. This is the inequality description, or the ray description looks like this. I'm going to keep saying ray this, ray that today, Ray. We're going to talk about you the whole time. So it's going to be the set of combinations of a bunch of generators where the coefficients have to be non-negative, and these guys, the VI's live in Rn. Okay? So for example, an example of a cone is something like this. A cone over a square. So this thing is infinite, keeps going in all directions, in these directions. And I'm defining it in two ways. I'm defining it as the points that satisfy these four inequalities. Okay. This thing is not hollow, right? It's full. Okay. So either you satisfy these four inequalities, that's one way to describe it, or another way to describe it is that you are a positive combination of the extremal rays, which in this case would be this one, this one, this one, and this one. One, two. Okay. So that's a cone. And the point of today's class is that affine semigroups and cones are closely related for a reason that maybe you can already tell. An affine semigroup looks like something like this. Right? So it's the natural combinations of some vectors that live in ZD. Remember that the word affine means that this you can think of as living inside Z to the D. Okay? So these are the combinations lambda 1 A1 up to lambda R AR, where the lambda i's are greater than or equal to 0 and they're integers. Okay? But of course, if you have an affine semigroup, then there's kind of a natural cone that you should consider, which is basically dropping the condition of being an integer in this combination and getting a cone. So it has a corresponding cone which, so if I call this guy Q, then one way of writing this guy is as the real non-negative combinations of Q. But what I mean is exactly this thing that I said. Okay, so it's almost the same definition, but you drop the condition of being an integral combination, and it can just be any positive combination. Okay? So I came into the classroom ahead of time to draw this fancy affine semigroup here. Okay? Does it look like a semigroup to you? So what's a semigroup? You need to be able to add things in here. So that, by the way, this is the origin. Right? So, well, it looks affine because it looks like it's in Z2, especially if I do this. Oh, fancy. So now you see also how I drew it. But I don't know, do you prefer to look at it in this way or should I turn it off? Really? I don't know what's better to see. Let's do this for now, and I'm going to turn it off in a second. Okay? So what's A? A is the whole grid. By the way, you'll realize that these squares were too big in the slide that I have. So A really is kind of the half grid here, where you have a grid that is twice as fine as this one, yeah? Because I should get all of these points on the grid. And Q is a sub-semigroup. And what that means is that I should be finitely generated. So we will check that. And you should have the property of being a semigroup. So if you add two of these guys, you don't fall out of Q. Okay? And that's something that's a little bit easier to check on the grid. For example, I don't know, if I add this point and this point, you're going to get this point. And if you take any 2 points here and you add them, you're going to get another one of the points that I drew. Okay? And my ray is basically the ray that you kind of see here. Where these are the two extreme rays of this semigroup. Right? And so this whole cone, this whole blue thing, is the cone that we're talking about here. Does that definition make sense to you guys? So it's the cone that you see if you just take spans instead of integer combinations. So I want to just say a couple of things about this. Maybe one thing I should say is just a definition. So I'm going to say that my semigroup is pointed if it doesn't contain A and minus A unless A is 0. Okay? So if whenever A and minus A are in the semigroup, sorry, 0, A must be 0. Okay. So what am I saying here? I'm saying that if I have the origin here, then I shouldn't have both A and minus A. If I had A and minus A, then I could take all their combinations and get this whole line. And so another way of thinking about this is that this cone doesn't contain any lines. In other words, it looks more like a cone because it has a point. That's why it's called pointed. Okay, so this means containing no lines. Okay? And so I want to prove a couple of things about this. So here's the first thing that I'd like to say. Any pointed affine semigroup has a unique minimal generating set. A unique minimal generating, finite by the way. Generating set. Okay. So you'll, by the way, the word finite is, I kind of put here for completeness, but it's kind of understood because in our definition of affine semigroup, we said that these guys were finitely generated. So it's clear that if you have a minimal generating set, then that thing is going to be finite. Okay? So really the interesting statement is that I have uniqueness here. Okay? And this is why I wanted to draw this example, because what I want us to do now is look at this thing that I'm claiming is a pointed affine semigroup. But I want you guys to tell me what the generators are. Okay? And according to this proposition, you can do it with without any further information. So what are the generators of Q? Now, remember that the way I did this last time was the other way around. I kind of drew these fat points in the bottom, and then I made all these smaller points on top. And so really what I'm asking you is what are the fat points in this picture that generate everything else? So I don't know. Can anybody tell me one of the generators? 2, 1. That thing obviously has to be a generator because this guy, you're not going to be able to write as a sum of smaller things. Okay. Anything else? 1, 2 kind of by symmetry. Two, 3 is this one. So why is this one in there? Well, because you can't get it from this one or from this one, or from anything below. Okay. Anything else? This one is twice this one. This one is this one plus this one. This one is twice this one. It looks like that might be it. But maybe not. Maybe this one is a generator. Who knows? Right? So how do we do this? The way that we do this is that we define a poset. Define a poset where the elements are Q. The elements are the elements of Q. And we're going to say that I is less than j in the poset if j minus I is in Q. So what I'm saying is, for example, that this guy is less than this guy in the poset. And the reason is that the difference between this guy and this guy is an element of Q. Okay. This element of Q. Or for example, I don't know. This thing is an edge of the poset. And the reason is that if I subtract, so this is I and this is j. If I take j minus I get 2, 3, which is this vector. It's in Q. Okay? Or, for example, this is an edge because the difference between this and this is this guy. Okay? And so I'm going to just draw all the edges of this poset. Well, not all of them. I would never finish, but some of them. And I'm going to color code them in this way, actually. So you know, if the difference is this blue vector, then I draw a blue edge like this. Right? So what do I get? I get something like this, this, like this. And so it looks like this, actually. It's kind of hard not to make a mistake, but anyway. Hopefully you see the point. Right? There's all these blue edges going in this direction. And then there's all these brown edges that go in this direction, and this gets trickier now. But something like this, something like this, something like this. You do all of them. And what is it that I want to say here? What I want to say is, so claim the minimal elements of this poset minus 0 are the minimal generating set. Okay. So what I'm doing is, I forget that 0 lives in this poset. Right? And then I look at the minimal elements of this poset. So in this case, if you do it, you'll see that there's only these 3 guys. Okay? Now, if you're a minimal element in this poset, then there's no way that you can be written as other things, right? Because, so if you're minimal, let's say if Q is minimal, and I was able to write it as, I don't know, a bunch of other generators, then there would be an edge between Q and Q minus A1. Right? If you could write Q equals A1 plus A2 plus etc., then this is A2 plus etc. So this is an element of Q, this is an element of Q, their difference is A1. And so this would be an edge of the poset, meaning that Q would not be minimal in the poset. So I'm just saying actually something that looks obvious to you guys, which is that if these guys are the lowest points, then how could you write them in terms of other ones if there's nothing below them? Okay? Now, if Q is not minimal, like this one is not minimal, then I want to prove that I'm able to write it in terms of minimal ones. How do I do it? Well, if this guy is not minimal, then it means that somebody's below it. And so let's just walk to one of the things below it, whichever one it is. Okay? Maybe it's this one. Okay? And then maybe I walk. So if this is minimal, I stop. If it's not minimal, I keep walking. And I just keep walking down the poset. Okay? Here, there's an edge between this guy and this guy, and to this one, and to this one. The point is that if you're not minimal, then you can kind of take a path to one of the minimal guys, and that path is exactly going to tell you how to write Q. Right? It's going to tell you write Q as, this was the purple guy, right? So purple guy plus brown guy plus blue guy plus blue guy plus blue guy, and that's your expression. Okay. So if Q is not minimal, then a path from Q to, it has to be Q minus A1, Q minus A2, etc., is going to tell you what to do. Will tell you how to write Q in terms of minimals. And that's the proof. Okay. So that's that. The brown one was, so you mean this one?
Yeah.
Why is it a generator? Well, what I'm saying is that this guy is minimal in this poset. In other words, I have no edges, I mean, other than 0, I have no edges going from something to it.
Okay, but then if you add him to the blue guy, you leave that column.
If you add him to the blue guy, you get this guy. Because this is brown plus blue. I mean, it's really a very delicate picture, right? And that's why I wanted to actually come and draw it with a grid, and even then it's a little bit hard to see. But it is true that if you take 2 points and here and you add them, you're not going to leave this cone. Okay. So that's the first thing that I wanted to tell you, is that these guys have a unique minimal generating set. Okay. Now I want to do something else. And that is that, do you see kind of the long-term behavior of this semigroup? Do you see how it kind of becomes periodic? I mean, if you look around here, all the points in Z2 are in the cone, are in the semigroup, sorry. So over here, everything is in, but actually over here, you get a bunch of gaps. Right? So actually, this is when I should turn this on, to see that there's all these gaps here, right? So there's all these integer points that are around here that are not in your semigroup, but they're in the cone. They're integer points. There's a bunch over here also. Okay? But actually, if you see what's missing, it's not much. What's missing is exactly a line like this. Yeah, maybe let me draw in what's missing. So this is missing, this is missing, this is missing, this is missing, this is missing. So that line is missing, okay? And this line is missing. Is that it? There's one more, right? This line is missing. Okay. And they're all parallel, and actually they're all parallel to the extreme ray. Okay. Is there anything else missing? I got a little worried for a second about whether this is missing, but this is not an integer point. So that's it, and 0 is always in. Okay.
And one word for that line.
1, 1. Oh yeah. This is another point I'm missing.
Yeah, the next
And it's part of this line. Okay. So what I want to discuss for the rest of the hour is basically some interesting results. And the point is basically that we actually don't understand this very well. I mean, there are some things we understand. For example, we understand why these holes follow these lines. But there are many interesting open problems about this, and so I want to tell you some things that we know, some things that we don't know. Okay? So maybe the first thing I'll do is just make it a definition. And it's called the saturation. I think it's a definition that makes sense. So if Q is an affine semigroup, let's say in ZD, then the saturation of Q is the cone of Q intersected with ZD. So what I'm saying is fill all the holes that you see. Okay? Put all those purple dots back in there, and now you get the saturation. Okay? So I just saturated my semigroup. Okay? And then I will say that the minimal generating set of this saturation is called the Hilbert basis of Q set. So in this case, the Hilbert basis is 2, 1. Well, let's think about this actually a little bit. Okay. Is this true? Actually, this is not true because I changed the semigroup and that changes the generators. Right? These black generators generated the black semigroup, not the purple semigroup. Okay? So what are the generators of the purple semigroup, which is the saturation? Well, I think we agree that you still need 2, 1, and you still need 1, 2. Do you need 2, 3? No, right? Because actually what you need now is 1, 1. Okay. And I think that once you have these 3, you get everything else. Do you agree? That's it. You have to stare at this picture and convince yourself that this is true. But it is true that these 3 guys generate the whole semigroup. So this is the saturation. And I just want to make another statement here. Which is the following. If C is a rational cone in RD. And what do I mean by rational? What I mean is that the extremal rays should be rational vectors. Okay. So the rays are, actually you can choose them to be integer vectors because the ray is basically any vector in this direction. So if this is 2/3, 1/3, multiplied by 3, and you get 2, 1. It doesn't really matter. So the rays are rational vectors. So C is a rational cone in RD, and A is a subgroup of ZD, then C intersect A is an affine semigroup. So what is the content of this theorem? What I'm saying is that if I take any subgroup of ZD, which is basically a grid, right? Subgroups of ZD are Z something, and it's basically some subgrid of this. It might be the whole grid, or it might be a subgrid, subgroup. And if you take any cone, like this one that we chose, then when you look at the points of the grid that are inside this cone, that's a semigroup. That's an affine semigroup. Does that sound plausible to you? I think it makes sense. You know, what do you need to be an affine semigroup? Well, you need to be a semigroup, meaning that if you add two guys, you stay in the cone. But this is a cone, and so whenever in a cone, if you take one vector and you add it to another vector of the cone, you're not going to leave the cone. So you're definitely a semigroup. You're definitely affine because this thing, by definition, lives in a grid. And actually, the one tricky thing to check is finitely generated. And I think it's something that makes sense. But that's basically the content of this is you have to prove that it's finitely generated. And this is not hard, and just for reasons of time, I'm going to skip it. But you can see it in the notes. I wrote it there. Okay? But finitely generated actually is because this is rational. And this is an interesting exercise that I think you should try. Is that this statement is false if you take, for example, this ray, this cone, where one ray is horizontal and the other one has slope √2. So you should look at this picture and convince yourself that this is not an affine semigroup because it's not finitely generated. And this just comes from the fact that there's no rational points on this line because √2 is not rational. And that means that actually you're going to need to pick generators that are closer and closer and closer to that line, but you can never choose anything on that line. I think this is a fun example to play with. Okay? But the point is that if it's rational, you don't have a problem. Okay. Okay. So I want to finish by going back to a case that, I mean, just to show it to you, that even in the simplest abelian group, which is Z. So what's an affine semigroup in Z? Well, it's a bunch of points, a bunch of integer points on a line. So let's talk about semigroups on a line. And you would think that this would be a trivial topic. I don't know. Does it sound trivial to you? Maybe it doesn't sound. It sounds as trivial as could be. But I'm going to show you that actually even this is a very interesting topic. So numerical semigroups. And when I say this, I mean Q, a subset of let's say the natural numbers. Okay? Because we want these guys to be pointed, and what does it mean to be pointed? It means you don't go positive and negative. Okay, so this thing has to start somewhere. Let's say it starts at 0 and it goes on. Okay? So what's a numerical semigroup? Well, let's say, for example, that you generate by 3 and 5. Okay, so what's the semigroup generated by 3 and 5? You have 0, you don't have 1. This is a bad picture, huh? It's not 3. Leave it to the combinatorialist to not be able to count to 3. So 1 is not in there, 2 is not in there, 3 is in there. 4 is not in there, 5 is in there, 6 is in there, 7 is not in there, 8 is in there, 9 is in there, 10 is in there, 11 is in there, 12 is in there, etc. So where did I should have written all of that. 8, 9, 10. Now what's the point? Once you know how to do 8, 9, and 10, which 3 plus 5, 3 plus 3 plus 3, 5 plus 5, then you can do everything, because if you have n, you have n plus 3. Okay. So the point is that you have the gaps are 1, 2, and 7. Okay? And 4. So here's, I think this is actually a very nice, it's a very old theorem, but I think it's very interesting. Why is it that I get eventually every number? It's because 3 and 5 are relatively prime. If they were both multiples of 3, then everything on this list would be a multiple of 3. So the interesting case is when A and B are coprime. Okay? So let's say you want to know what the gaps are. Well, it turns out that you can say exactly how many gaps there are for A and B. And the number of gaps is A minus 1 times B minus 1 over 2. So if I did this correctly, here I should have 3 minus 1 is 2, 5 minus 1 is 4, 2 times 4 is 8, divided by 2, 4 gaps. Should we call them? Actually, this is a little bit misleading because a gap sounds like a continuous thing. So let's say number of holes. Okay, so a hole is a missing element. Okay, and now what's the last hole? It turns out that you can also say explicitly what this is. And this is AB minus A minus B. In this case, 3 times 5 is 15, minus 3 is 12, minus 5 is 7. So that's the last gap. So I think this is very pretty, that you can say exactly what these numbers are. It's not terribly difficult to show, but it's not so easy either. I think this would be a nice homework problem that you actually have to think about and prove. It's tricky. Okay? So, but this is a theorem, I think, due to Frobenius originally. I'm not sure. But the point that I want to make is that this is known for 2 generators, and already for 3 generators, this is wide open to understand these questions. And actually, some of the best results on this are by Matt Beck, so he can tell you more about these kinds of questions, about Frobenius numbers. But the point is that, already for 3 generators on the line, there are open problems. It means that we actually know very little about this. This is a subtle question. So that's one thing that I wanted to tell you about this. And the other thing that I wanted to tell you is an open problem that I just heard 2 days ago that I'm excited about. I think this is a really cool problem. So let's say that A sub n is the number of numerical semigroups having exactly n holes. So for example, this guy is a numerical semigroup with 4 holes, so this guy contributes towards A4. Okay, but there are going to be other semigroups that have exactly 4 holes. By the way, it shouldn't be obvious to you that this number is finite, but it's true. There is a finite number of semigroups with 4 holes, and we call this number A sub 4. You can imagine that this is a very difficult number to compute. Actually, I don't know that there's any. Maybe part of the question is, how do you find a good algorithm to compute this number? How can you list all the semigroups with n holes? It's a hard question. And if you asked me 2 days ago, I would have told you this is kind of a hopeless question. You're not going to get a nice answer. But there's this amazing conjecture. This is conjecture is due to someone called Bras Amoros in Spain. Amoros. And this conjecture is from last year, meaning that people haven't had so much time to think about it. The conjecture says that if you take the number an and you divide it by an minus 1, and you take the limit of this, then this thing has a limit, and the limit is the golden ratio. That's a crazy conjecture. It's a beautiful conjecture. It basically must, I mean, if the conjecture is true, that means that we don't understand this at all yet, right? Because somehow there must be some structure embedded in this quantity for which the golden ratio comes up. But you guys are aware that this golden ratio appears in many places, and probably most relevant to us is in Fibonacci numbers, right? So if this was the Fibonacci number n and the Fibonacci number n minus 1, then you would have this property. Okay? And so this seems to indicate that these numbers are closely related to Fibonacci numbers. But how? It's open. Like I said, because this is only a year old, maybe it's not that hard. Who knows? But so if you want to read more about this, the best results so far are by Elizalde, who's this classmate of mine, actually. And he's very good, so this means this is not an easy question, but who knows? Maybe this question just needs a new point of view, and maybe after taking this class you have that point of view. I don't know. One can always hope. So there you can see the statement of the conjecture and the best known results about it. That's interesting. So that's it. So basically what that means is that affine semigroups are pretty things. The question of where the holes are is a very subtle question. And so that's why actually very often what we will want to do is saturate and then ask questions about the saturated guy, because those guys are more manageable. The whole questions, I think that this already shows that we don't even understand them on the line. So maybe we're not ready to ask the difficult questions in d dimensions. Okay, so I'm actually going to do the teaching evaluation thing today. So pass these around quickly. If I could get a volunteer. Where did they go? Oh, here. I'm sorry?
Every one of my classes.
Yeah? We got them yesterday. Yeah, you can email the homework at midnight. So I need a volunteer. If I need, so just give these to. You could please pass these around. Well, I need just. Now I'm not supposed to know anything about what you wrote, which is a good thing. So that means we'll say it out loud because you're on camera still. But that might work. There's pencils here. So you guys know the drill, but one thing that I want to ask you, well, there aren't that many pencils, so if you have a pencil, please use it. So one thing is that if you don't do this with a pencil, it's not going to show up. So please use a pencil. And the other thing is that, you know, numbers are nice, useful, whatever, but what I'm really, really interested in is feedback. So please write as much as you can about this, about how we can, how I can improve what worked, what didn't work. I will just write the number of the class, 850-01. What else do you need to know? You probably need to know how to spell my name correctly. So only one L is the most common misspelling. Anything else you need to know? Is one good or bad?
One is good.
That's always the hardest thing. One is good, 5 is bad. Kind of the opposite of what you would think. But yeah, please write as much as you can about the homework, online thing, the forum, the project. Any feedback that you might give me is very useful. Did everybody give you their homework that wanted to give it to me? And this is the previous one. Fangy, Elizabeth.